again, my friends. Once more, welcome back to Leopard Street, land of intrigue and noisy electronics. This one, we're back with the turntable, which as you can see is rotating. And since you can hear me, you can hear it's not screaming for mercy. So what we're going to do is have a little look at what I had to do that. Then we have a little look at the next problem. Noisy electronics. Stick around. This is Leopard Street. Okay, so previous video, this would turn, and if I connected it to the layout power supply, it screamed for mercy and didn't rotate. But if I connected it to an external power supply, it worked. Bit weird. I've fixed that. What I'm going to do is go to the desk and we have a look at what the problem was. Well, that's not what the problem was. What I think the problem was, and this is hypothesis, I've fixed it, so I think I've got the diagnosis correct. Let's go and have a look. Let's get to the desk. Okay, here we are at the desk. Now, if you've seen Ian's channel on Trains of Thought, you'll recognise this sort of idea. 3x5 index cards. I got about 600 of these as a sample for review from Amazon. I'm part of the Vine program, if that makes sense. Anyway, they're easy to use than bits of paper. So what I'm going to do, I'm going to grab one of these and have a little look at what we had. So I had a 12 volt power supply. So we've got ground, 12 volt, and between there is a plus minus. That's my power supply. And it was coming along here quite happily. Now, I suspect what's happening, because this goes into what can only be referred to as box of magic. And it then comes out into a couple of motor coils. And the way this thing works, by energizing these coils in different ways, it turns the motor. And it's energizing these on, off, on, off, on, off. Or sometimes fully on, sometimes fully off. Different steps. And the way it does it is by taking its power supply that comes in and just turning it on and off to the different coils. And it can do them that way around, it can do them the other way around, all sorts of stuff. So what it needs is a clean power supply. That is one where the voltage coming in, I'll draw a little graph on it, is that at 12 volts. Now what I think I had is that. So it's nominally 12 volts, but it's creating noise on here. So when this says go to a certain point, it might be a bit higher, it might be a bit lower. And it's causing a problem. Now that's what I thought was happening. Just moving a bit of sellotape on my desk. Now, that's actually quite a common problem. Noisy power supplies. I thought, well, what do you normally do to deal with a noisy power supply? What you do is you put a filter into it. So the first thing I did, I thought I'm going to need a capacitor. Don't need the resistor. I could put it, you could make they call it like an RC network. I don't really need that. I just need a bit of smoothing. So I thought to myself, first off, well, I'm going to come along here to my output. And what I'm going to do is I'm going to whack a capacitor in. Not sure what value. I thought because I'm using it as a power supply smoothing capacitor, I want it to be a decent size. And what this will do, this will take this squiggly voltage and it'll smooth it. It won't turn it completely flat, but it'll smooth it out. Because when this goes higher, a little bit of current will flow into there. When it goes lower, a little bit of current will flow back that way, and it'll smooth the effect out. Thought, right. But what I don't want this to happen, C for capacitor. What I don't want this to be doing is trying to fix the problem on the whole layout. All I really care about is feeding the turntable motor. So what I also wanted was a diode to sit there, just a normal diode. This is a 4 amp supply. The stepper motor doesn't take anything like 4 amps. It's about an amp, amp and a half. So I've made that a 3 amp rectifier diode because that is what I've got. Now, the first thing I did, I didn't put the capacitor in. I just put this in. Why not give it a try? That nearly fixed the problem, which is a bit... And what it means is it's stopping the sort of the effects of this going back the other way. And I turned the motor on, and it turned, and it was silent. Brilliant. I told the motor to stop, and it went, and then stopped. Start it up, turned, stop. Put the capacitor in, and the one I've put in is a 2200 microfarad. It's a chunky capacitor. And now the motor turns completely silently. So that has worked. Sometimes you might want a big capacitor, and you might also want a diddy one, 100 nanofarad, something like that, next to it. Because they charge at different rates. So this little capacitor will be very good at getting rid of high frequency problems. This will smooth out larger variations. So, but by brute force over ignorance and just blind experimentation, I have smoothed the power supply. I got the idea actually because years back, I mean, you would have start with another bit. So we're not limited on card. You would have an input power supply. You would put that into a bridge rectifier, which is that way. Try and sort this out. Something like that, and then that comes off there. That comes off there, and there's a power supply. And if you put in a sine wave into that, that's over 0. What you'll get out here looks like that. And the way you fix that is, you guess what? You put a big capacitor there. Sometimes multiple. A lot depends on what you're doing. You put a couple of capacitors in, and then what you get at the end of that is something that looks like that. You get a bit of a ripple, but it's usually pretty smooth. You can smooth it out a bit more, you can filter it a bit more, but that's that. So that gave me a smooth power supply. So now it works off the layout. So if we go back over here, we'll have another look. Now, back with handheld camera, because there's a few other things I want to show. So here we are, and it's turning quite smoothly. And it's at the right height. It still rubs a little here. I need to take the bridge deck out again and sand one end. I think it's this end that needs sanding. This is on here to remind me which end the magnet is at, because that's the next problem. So I set this up. Now I've modified the software. This is now talking over its Wi-Fi. It is talking to MQTT. I send this a command. When it switches on, I've got a software state machine. When this is working properly, I'll go through the code. But when it comes on, it starts up in startup mode. And all it does in startup mode is sit there. When I turn this thing on, I don't want it to do anything. Reason for that, say I have to power the layout down while Cheshire here is partially on the turntable. When I switch the layout back on, the last thing I want this thing to do is start moving when there might be a train half on, half off. So by default, it does nothing. I can then send it some commands. At the moment, it understands the letter S, which says startup, and that puts it back into its starting mode. The letter T, which is test, and that's what it's doing here. Test mode, all it does is say, wherever I started from is my reference point, and it will go 360 degrees one way and 360 degrees the other. That's all it does. But I'm using it just to test whether it works. Now, what this is quite useful for, when you find, get the Allen key, when we find out where it stops over there. So that was where it stopped. So it'll go round and it'll stop around there and it'll bounce back. The idea behind that is run it for an hour or two and see, is it still stopping in the same place? If it is, it's fine. If it's not, it's slipping somewhere. And if it's slipping, it's probably, if I come down here, that coupling there. There's a little green ring above it. The green ring is there because these little wires that come down were getting caught in part of this coupling. Yeah, you may be able to see it when it comes back around. Basically, there's a vertical gap in it, and it was just catching the wire. So I just shoved a small plastic washer on top. So that works. Now that was the first bit. It understands the command D, which disables the stepper motor. The reason I did that was because if I want to do any work on this, what I don't want to have to do is go around there, crawl under the layout, turn it off, then come back around here, do something and repeat. So D disables the stepper motor, E enables the stepper motor, so I can turn the coils on and off quite easily. Brilliant. I also made it a little bit quieter. You'll notice not all of the wheels are turning. It rides a little bit above the running rail, only a little bit. I quietened it down a bit by adding a drop of oil onto all the bearings of the wheels. They do all turn at some point. Some of the noise this thing used to make was it dragging plastic along and the vibration just screeching. So I dealt with that. And I put a dab of oil. You can sort of see that. A little bit shiny on there. And I put a dab of oil actually on the wheels. Now what it's doing is rubbing the paint off the wheels slowly. It is molded. The wheels are molded in a dark coloured plastic, so that shouldn't matter. It'll rub it off the rail as well, which is a bit annoying, but never mind. So what's next? Well, I can't drive a train on here yet. I can't connect the rails until I can hook up a relay. Now on here, there's space to put a relay circuit. That's fine. There's a problem. You may know I've got a sensor and it lives. I'm just going to find it because I can find it. It lives about there. Buried in the wall of this, there is a Hall effect sensor. This end has a magnet. So I thought, well, all right, I know that works, so I can hook that up. So I did. And I created a calibration circuit. And what it says is rotate anti-clockwise until you find the sensor and then stop. And that's all it does. And I told that to go, and it just sat there and didn't do anything. Yeah. Spent a bit of time playing around with it, and I thought, I'm going to look at what this sensor's doing because I want to see what this sensor's doing. Now, the sensor, it's basically a transistor. If I just grab my little bit of, grab a little bit of card and a pen, I can show you what that does. I'm trying to find a pen. Just bear with me a second. I'll move the coaling stage so I've got a little bit of space here. So what the Hall effect sensor does, it's basically a transistor like that. That goes to ground and you put a supply in at the top. So that's plus voltage. You look out there, you have a pull-up resistor, 10K, whatever, 10K, 100K, doesn't matter what it is. And that's where you measure from. So normally, that's not conducting. So your output is a high voltage, your supply voltage. When that does conduct, that just says, I go to ground. So that goes down to 0. So it's an active low sensor. Well, okay, well, I'm reading that with my ESP32 over here. I haven't actually got that bit in. I've used the internal bit that says pull up internally. So, but it's there and it should work. And when I tested this originally, literally, I mean, just when I installed it and started twiddling the deck around, worked fine. Now it doesn't work. What the hell's going on here? But the table wasn't moving at all. If the sensor doesn't work, what it should do is spin continuously. So I thought, I'm going to go back to my little circuit here, and I'm going to put in an LED. So I did. LED. And I put it on this side because what I want it to do is be off when that is at logic high and light up when that is at logic low. So basically when the sensor is active, the LED comes on. Brilliant. How hard can it be? That's the LED. See it flickering? It's not at full brightness. The wheel's about to go round. You'll see it at full brightness in a sec, and it goes round. Look down from a, yeah, well, I'll hold it on this angle. You'll be able to see the difference. I went with a white one so I could see it from the desk. Here we go. It'll come around in a sec. See that bright flash? That's what it should do. It's flickering. That'd be why things were working. And what I also noticed, this is another bit of diagnosis, this is the speed the table is supposed to rotate at. It was going about half that speed, and it was juddering a lot, but it was rotating. It was fine until I put the code in to look at the sensor. So I thought, it's got to be something to do with the sensor. Now, I've got this set up with what's called an interrupt. So when this sensor changes, there's a little bit of code that runs. All it actually does is set a flag and go, woo, I've changed. And then elsewhere in the programming loop, something says, it has changed, I shall do something. The interrupts, you want to be very, very quick code. So I thought, well, what's happening? And the reason the thing's slow to a crawl, I've put some code in to say, when that changes, send out an MQTT command. I want to see what this sensor is doing. This was before I put the LED in. So every single time that LED flickers on and off, that's what it was doing. It was completely swamping the Wi-Fi. Yeah. Problem. Need to do something about that. Now, the interesting bit, if I come over here, I'm going to turn the stepper motor off. I'm going to put it out of test mode. I'll turn the stepper motor off. This is literally how I'm controlling it at the moment. I'm using MQTT Explorer. So I'll put that in S. So when I publish this, the table stops. What I can now do is come over here and say D, because if we look, that ain't flickering anymore. Even with the, I don't need to disable the thing. That ain't flickering. What we've got is noise. And in this case, it's not really electrical noise as such. It's magnetic noise. This thing is picking up interference from the stepper motor. Annoying. Can't turn that around for it. Yeah, picked up my Allen key. But if I take the Allen key off the bastard magnet, I've stopped it in the wrong place. But there we are. See, I've got a big strong magnet here, and I can put in the here, and I can trigger that. As you can see, it starts to flicker, and then it comes on. Now this sensor, I forget what sort it is. It is supposed to be an on-off sensor, so it should go like that when it detects something, or the other way around. So it's either doing that as the magnet intensifies. I don't know. I don't think it's doing that. Or what I suspect it's doing is going like that. So when the magnet's there, it's a very strong signal. It's on all the time. Otherwise, it's just picking up the interference from the coils. Let's go back to the desk and have a little think. Okay, so what can I do with this thing? Well, currently, I have my sensor, and I'm bringing that out, and that's coming out into my microcontroller. And here we have a magnet. And I make no pretext at knowing how magnets work. There are all sorts of memes online about how the magnets work and who you should ask about such things. I do not know how magnets work. As far as I'm concerned, a magnet is magic. Anyway, so we have a ground line there. This sensor also has a feed line. So up here we have 3.3 volts in this case. And that goes into the sensor as well. And that's basically what I've got. That looks remarkably similar to a switch. And if you've ever used a switch with a microcontroller, you'll know you expect a switch like so. It's open or it's a push button. And you will expect you're going to go along and I'm going to close the switch, ding, and it'll do that. Possibly not going backwards, it'll be vertical. Think about it slightly more. You'll think what it might actually do is that, because it will take a little bit of time for the signal to change. You always get a signal change. Brilliant. That's lovely. That'll work really, really well. I think I'm about to be joined by my furry helper, who, if she gets in the way, will be told to move. Oh, she's going back under the desk now. What you actually get is this. It's called bouncing. And as you close this, the contacts will start making and breaking briefly before it sets in. A good switch will bounce once or twice. A bad switch could bounce 20 or 30 times. And you can actually test that. If you set up some microcontroller code, so you have that go into your MCU, and you set up an interrupt, and all you have that interrupt do is when it triggers, it takes a variable V and it goes, add 1 to it. Get off. I'm getting a claws into my leg now. And then you say, right, I'm going to run that for a few seconds. I'm going to press the switch. And you come back in and you think, well, V should be equal to 1. It should have gone once. And you'll say, oh, it's 10 times. It's 20 times. It's 5 times. Oh. And you can use it. You can test it quite easily. You press a button and you say, I'm going to press this button and I'm going to increment something by 1. And it'll go up by 3 or 4. Bouncing switch. Very common problem. And there's a way of dealing with it. And what I'm going to do is I'm going to use the same way of dealing with it with this. Now, I don't know if this is going to work, but I'm going to try. So the first step is I need to add a pull-up resistor here. I'm going to use a 10K because I normally use a 10K for a switch. I might need to change it in this case. The job of that is to make sure this point sits at 3.3 volts when that, as if that's not there. And when this does conduct, it limits the amount of current flowing this way. That's its job. A small resistor there, you'll get more current flow, but it'll go from 0 to whatever the current flow is much faster. Then there's no such thing as a pure resistor. We love to think of these things as pure resistors. A resistor has a capacitive effect and an inductive effect. So I'm not going into all of that. I studied it for years and it made my head hurt. Yeah. So you put a small value there, you can make this go quicker. You see this if you're starting to use phototransistors and you're trying to measure a quick pulse. I did this with the Scalextrics system. Hornby do a digital Scalextrics. We're going to a quicker side. And what you've got is a car, which looks a bit like that. Hopefully looks a little bit better than that. And you've got the track. And underneath the car, there's an infrared LED that flashes. And what that's sending out is a little signal, and it basically says, I am car, and there's car 1 to 6, and there's 2 bits of information it can send. I think it's 2. Yeah, it sends its number, and it sends, I want to change lane. Yeah, there's 2. I want to change lane, and I want to brake. I think it's that, or it might just be change lane. And underneath the track, there's a receiver. And this is where you get the Scalextrics digital, where you've got a piece of track that does that. Looks rather familiar if you're model railway. You basically got a set of points there and there. The other end's passive. And there's a little sensor as you come in. And if the car is going, I want to change lane, it'll change lane. And what this has to do is read this pulse. Now think about it, the car's going past. In real terms, I don't know what the scale speed is, but in real terms, Scalextric cars, 5-6 meters per second is not unreasonable. I did some timing testing and I was getting cars running at 4.5-5 meters per second quite easily. So this has got to pick it up, and it's a single sensor. It's got to pick it up quickly. So that's flashing fast. So you make that with a phototransistor, and if you put a 10K resistor on there, it doesn't work. It doesn't respond quick enough. So you put a 1K in, to get a bit more current. You're talking a couple of milliamps. It's not. I mean, it'd be suitable for putting an LED in there. It's not blinding, but that's how you go with that. And then what you do is you come along here, and now I've got a bouncy signal here still. That's done nothing for the signal bouncing. All this is doing is replacing the pull-up resistor I had inside the ESP32. I now need it to be here. So along here, what I'm going to do is I'm going to put in another resistor. Call it R. And this is going to come out here. And here, I'm going to put in a capacitor. I'm going to call it C. Now, for a switch, what I normally do is I'll make R another 10k resistor, and I'll make C a 100 nanofarad capacitor. And the reason I choose those two is because I've got a lot of them. That's the reasoning. The larger those two values are, the longer the pulse has to be before this circuit will see it. And what basically happens is you switch this thing on. Another piece of card. I love these bits of card. So here's your graph, and it comes along, and you say, right, at that time period, I'm going to press that switch. Well, so I'm going to switch it on at this time. So the voltage here starts off and think, oh, brilliant, that capacitor's charging. So the voltage there is basically 0 because it's connected to ground. As that charges, the voltage does that. And these resistors, which limit the current, will vary how long that goes, and the size of the capacitor will limit that. So that'll switch on. At this time, somebody presses the switch, puts the hand over the infrared sensor, whatever. Right. So this is now going to conduct here. So this is going to drain back out that way. So again, this is going to limit it draining. This one will affect it charging. This one, well, both will affect it charging. This one alone affects it draining. And what it'll do is it'll drain. So the voltage at this point will start at this point, and it'll drop quite quickly. And it'll tail off, and it'll do that. Well, say you've got that bouncing effect. What you'll find is your voltage comes up, and I'll do another line, comes up here, and it's in its steady state, and it'll start doing this along the top, and then eventually it'll drop down like so. Now the key bit is whatever you've got feeding off this. I mean, that is your supply voltage. Well, typically most processors, they have what they call a hysteresis loop or similar loop. So you will have 0, 3.3, and where these lines are varies. But you have a signal that does that, or whatever it is. If it is below that voltage, that is low. If it is above that voltage, that is high. And if it's in the middle, we don't know. And the component data sheet will tell you what these two thresholds are. But if it's above that voltage, it is guaranteed to say high. Below that voltage, guaranteed to say low. In between, it could say either. And you'll find some chips will read high, some will read low, whatever. But as you can see, if you're up here and you've got a little bit of rippling like that, doesn't matter. Until it gets down here, it won't register as low. And ideally, you want to go through that bit as quickly as you can, because that's undefined behavior. So you want to get down to here. So you want this to effectively, because you're sort of talking this region here, you don't want this time base to be too long, because if it is, you'll spend too long in this region. You don't want it to be too short, because the shorter it is, the deeper these go, and they might go below here. So you have to fiddle with it. I'm being watched again. I'm being meowed at. What? Meow. Get off. Ouch. You claw out my leg. Come on, shoo. You're not coming on the desk. Go away. Come on, go away. Shoo. Shoo, 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 shoo. Yeah, flipping kitten. Right. There's another piece of this. Now, this voltage, as we've seen, is a curve. Right. I don't want a curve. So what I'm going to do is I'm going to put another component in here. And it's an inverter, but it's a special sort of inverter. This is a Schmidt trigger. So if we go back to another piece here, and we have this. Now our signal voltage is going to do that, for example. So that is the input voltage. We don't want that. We just want a high or a low. So what you do is you put a Schmitt trigger in. And it says it has 2 threshold voltages. Again, always 2 threshold voltages. This one works a little bit differently. So we'll have up here what the output does. So it comes along here and it gets to this point here. That point, is it the bottom point? I think it's the bottom point. It'll get to the low point and it'll go tunk. I've seen the signal is now high. No, it's the other way around. Forgive me. So it goes up here and it says the signal is high. Now the point is, if that's got a little bit of a ripple on it, it doesn't care. It's not going to go below this low point and it'll go high. But when it gets to there, it'll stay high until it gets to there. Then it comes down. And this is where you've got the little symbol. The voltage has to go higher to trigger it and then lower again to stop it. And if the signal varies inside this area here, nothing matters. But if it got to that point initially, it would stay low. If it peaked and then came down again, it'll stay high. So what we do is we put the Schmitt trigger in here. But the other thing that does is that gives you a very, very sharp changeover time. So we put that in there, and then this becomes our output. Out. And now our input can be a bit ripply and peaking and troughing. And what we get out here will be that, in theory. There is one other little bit that you need. And I say need, you don't need it, but it can help. And you put a diode there. What this does is mean this capacitor only is the one charging this, because the current will flow through there quite happily. This resistor here is now just the discharge resistor. So I need to build that. Now, that little beast, it is a 7414. 7404 is just an inverter. 7414 is an inverter with a Schmitt trigger. Now, what this means is, this is normally high until that triggers, and then it will go low. Well, that inverts it. So this is now going to go high, active high. So I need to change the code a little bit because it's now looking at a high signal rather than a low signal. If that matters, you stick another inverter in. So I'm going to get the bits. We're going to have a look at building one of those. I'm going to have to build it on the layout because I don't want to have to de-wire everything. So I'm going to find the pieces and we'll get back to the layout and have a look. Okay, back following the what can loosely refer to as the finding of the implements. So 7414. Here we have one here. I need to find somewhere to put it, and I'm going to put it here. I don't know where I put it. I just need to put it somewhere where I've got space to put the relay module in later. This is a 14-pin chip, and it has a pin out that looks like that, if that's showing up. So what I need to do, I've got a cat trying to get in the ceiling again. She's a little sod. She really is. Her stardom has gone to her head. I need to connect a few of these. There we are. Cat in the ceiling again. And you get a couple of these up here. And I'm just making my own jumpers. You can get boxes of these little jumper wires made. I was looking with this at just using the DuPont cables. However, it's hard enough to see what I'm doing anyway. So I'm just going to just make a few of these. Yeah. Now, this is all experimentation. Kelly has quite rightly pointed out this all could be so much simpler by just buying a turntable and operating it by hand. You're, of course, entirely correct. That would be a lot more simple, but where's the fun in simple? Right, that's power. I need to ground. This has actually got 6 of these little things built into it, which is actually going to be quite useful. Reason being, I've also got some switches I want to add to this thing. And they could do with debouncing as well. And if I've got one of these 7414s here, I might as well do it and use it. I can hear a cat above me now. She really is ceiling cat. She loves it up there. I don't know if there's spiders up there or what that she can chase, but As long as she doesn't start biting wires, we'll be all right. Just get the end of this. So what I need to do, there's a few things I need to do with this little circuit. If I can persuade this bit of wire to cut. Not sure what's up with it. So we go. Yeah. But the idea here is this will hopefully... I give up. I'm going to show another piece of wire. Yeah, anyway. Right, that's that bit. Chop that to there like so. Ah, dear. It's all good stuff. Except the bits that aren't. The problem with a cat pandering about on bits of plywood over your head is you can hear it, but you can't see it. So, the one thing to note with this chip, obviously I'm not using all 6 of the inverters it's got. And they're connected, so like pin 1 goes to pin 2, that's an inverter. The datasheet says, and because the datasheet says I'm going to, all the inputs you're not using tie to ground. Basically, because if you don't, you've got floating inputs, and with the floating input, you never know quite what it's going to do. So I'm going to use inverter 1 for this, 1 of 6. So I'm going to wire this up. I'll be back in a sec when I've got this wired, and we'll have a little look. Okay, back with this wired up. So what we've got, this pointy stick here, this yellow wire here is coming from the sensor. That goes in here. It has a 10k resistor to positive voltage. It has a 10k resistor and a diode in parallel coming down to where this orange cable is. That also goes to ground via the capacitor, which is this little circuit here. So that's all of this bit here. That trigger is on there. Then the green cable is the output, and I've got that at the moment just going to an LED. So what I'm going to do, I'm just going to move this slightly just in case the layout starts deciding it wants to play while I'm doing this. I am going to turn the layout on, and we're going to have a little look and see what that does, if it does anything. Because while I was doing all of this, I had the layout powered down, which is a good idea. You're playing with electronics, switch them off before you start plugging and unplugging things. Turn the layout on. And assuming I don't have magic smoke escaping, because I can't see it while I'm turning the layout on, we shall have a little look. Now, incidentally, over here, this is ye chonky. Let's angle that slightly so you can see. Chonky capacitor, chonky diode on the back of it. So, what to do, turn that, because that starts up, switched off, which seems a little odd, but anyway, if I run this round here, I should. Something's getting rather warm. And because something's getting rather warm, I'm going to turn it off. I'm going to find out what it is I've done that's wrong. Off. So yes, I can feel that's got a little bit warm. So that tells me something somewhere is wrong. So yeah, try that. I know what the problem is. I've plugged this in backwards. I'm going to hope I've not destroyed it. It is rather warm. Hopefully it's not dead though. It actually should be in that way round. It's my fault for trying to wire the thing upside down while I'm looking at it. Right. Don't wire them in backwards. Let's see if this works. If it doesn't work, I'll have to go and find another one. Which is going to be interesting. I do have a whole box of the blasted things somewhere, but I'm not sure where it is. Something to be aware of, though. Yeah, these chips, they don't like being plugged in backwards. So don't plug them in backwards. Right, everything's now powered up. That's switched on. Right, now, see the LED? So the circuit is working with regard to that. The motor coils are currently powered up. So what I'm now going to do is tell the turntable to move. I'm going to move this so you can see the turntable and the LED. So we're watching for this LED, which if it does that, I'm happy with as the table goes round. So I'm now going to do this. And I come back over here. I go T, the thing in test mode, and it starts spinning. And critically, this isn't flashing anymore, which is quite useful, because if this works and it actually detects the thing, I'm quite happy. So look, as it comes round, it's round this area here somewhere. Does it go pling? Yes, it does. That works. I'm happy with that. Right, what I'm going to do, I'm going to turn it off. I'm going to re-rig this to get it to talk to the chip again, and I'll be back. So I'm going to go and do that. Okay, up and running, wired up the right way around. Made 2 slight changes. I powered it up and I tested it. As it came around here, it flickered briefly. Came in, flickered once or twice. You can see the light coming on down here. I'll move the magnet. And then it went. Now that's still not good enough. So what I did is I've changed the 100 nanofarad capacitor for a 1 microfarad capacitor. So it should be about, need a pulse about 10 times as long before it triggers. And as long as it captures the pulse and it does it predictably, it doesn't actually matter if it's right at the very beginning or slightly inwards. It doesn't matter. And I've moved the 100 nanofarad down here to decouple the 7414. So as this comes round, light comes on, light goes off. That's feeding back. So what I now need to do, now I've got that working, well, there's 2 things I need to do. Firstly, I need an ice cream because it's warm again today. Here it comes again. Like, I now need to adapt the code to take advantage of that and zero it. I've started writing something, it's not working properly yet. I need to debug it so that I can tell it calibrate, go around there, find where the light comes on and stop. That's then my 0 point. That's what I need to do. So I'm going to go and have a play with that, and I'm going to come back. Cat still in ceiling. I can hear you. Yes, I can hear you up there, you little sod. Right. Yeah, I'm going to go have an ice cream. I'm going to sort this out, and then I'm going to be back. Yeah, a little bit of code finagling later. So, we've just switched on. Magnet's over there. The calibration point is around here. You can see the little light comes on down in the bottom corner of the screen. I've tried to position it so you can see things. What I'm now going to do is run the calibration routine. And what it should do is turn until it finds the sensor and stop. So that's what I'm going to tell it to do. So I come over here and I go C, which tells it calibrate, and off we go. And it should run round here until it just trips that sensor and then it'll stop. There we are, lights on. So what I'm now going to do is mark, I see the light's gone off now. The light's gone off because it's only just on the very edge of the sensor. So I've positioned that bit of rail. In fact, what I'm going to do is use this camera to good effect. I'm going to look straight down it like that. So I've got that there. And in fact, I'm actually going to put it at this end because that'll make it a little bit easier for you to see, as well as probably for me to see. That's there I want it to. And the idea is that is lined up as if you're going to drive onto it. Possibly not perfectly lined up. I just adjust this very slightly. Try to adjust it very slightly. What I'm going to do is put that there. I'm going to stick the wagon on it. I'm just going to. There we go. So that'll roll on and off. Now, if I now tell that to go into its test mode, it should rotate 360 degrees, stop, 360 degrees, stop. I hope. We shall see. But that should now be its position 0. And if it is, what that means is I've got a reference point. And having a reference point means I can tell it to move relative to that reference point, which is going to be the next stage of this. That'll be the next video. If this works, I'm happy. I'm just going to let it run for a little bit. And I want to see if it rotates to that point, fine. If it drifts, I need to know. But the next stage on this, I mean, I'm actually quite pleased. Yeah, I've got a cat down by my leg again. Here we go. Are we going to stop lined up on this little temporary piece of track? Ding. Hard to tell because it doesn't pause. I could probably actually do with getting it to pause when it gets through there. That wouldn't be hard to do, actually. I'll just add another little state that's test pause. It goes into that and then it returns. But yeah, that seems to be working quite nicely now. It's rotating smoothly. It's rotating quietly. I mean, by quietly, I mean this. I mean, there's the odd little click here and there, but that's just as bits of plastic are going past each other. I'm quite happy with that. The little sensor light comes on every once in a while. I'm fairly happy with that. Essentially, what I know is these three tracks here are all wired up brown, blue, brown, blue, brown, blue. And we go all the way around here and it's brown this rail. Here it's brown, blue. So this track is wired the inverse of these. So I need to set a position. I mean, this is my reference point. If I say, basically, if you're plus or minus so much from that, a relay needs to click. And the way I'm going to do that, I'll test that to start with by putting another LED on this little board down I've built. And then we'll see. And if it works correctly, I'll be able to put a relay in. I'll be able to get that reversing current. I've not decided yet. I'm very tempted to actually put two relays in and have one that says power off, so that when the thing first starts up, I can make sure the power to the turntable deck is off. This is because I've sort of noted I don't want to be able to drive trains on and off of this, but if a train is partway on and off the deck and the power comes on and the deck is in the wrong orientation, or the relay hasn't tricked yet because it doesn't know where it is, I'll get a short circuit. So having the ability to say, I do not want the power to be on at all to start with is worthwhile. But, yeah, so I'm going to leave this one at this. I'm going to let this run for a bit and I'm going to see just how accurate it is. We'll have a look as it comes around this time here, how good it looks. Yeah, I'm just going to meow out again. I think it wants fuss. It'll get some fuss in a sec. Ding. That appears to be okay. The test, once it's set up, is basically to just leave it running back and forth for like an hour or so and see whether it's still lining up correctly at the end of that. And if it is, brilliant. And if it's not, there's a problem with it drifting somewhere. But that's quite good. So yeah, with that, that's this one. So in here, what we've had a look at is how to smooth a power supply. So I've got my 12-volt supply to this thing now working without it screaming for mercy, which I'm quite pleased with. And how to debounce a sensor input in such a way that we can use it to generate a reference point, which I'm quite pleased with. So yeah. As usual, likes, comments, shares, subscriptions, more than welcome. Any comments on, do you think this turntable's spinning too quickly? Once I've got it finally working, I may put like a soft start and a soft stop in it, but I think that's not an unreasonable speed to go at. Some turntables I think go faster than others. Basically, I don't want it to take forever to turn the train round. So thoughts appreciated on that. Otherwise, enjoy the rest of your week. I'll catch you in the next one. Thank you very much and goodbye.